Hi everyone, my name is Feng Xiao. So this is of course not only my work, but also the work of my wonderful co-authors Jinquan Zhang, Jianwei Huang, Guofei Dinghao and Peng from Penn State and Texas A&M. Today, I'm going to talk about some interesting new attacks against SDN controllers. I would like to start with a little background in SDN. SDN is a network paradigm that separates the control logics from the data plane. And there is a networking OS called SDN controller in the control plane. This controller will be responsible for most network functionalities, such as forwarding and load balancing policies. To manage the network devices, such as switches and hosts, the centralized control plane employs a series of open standard protocols like OpenFlow netconf to communicate with the data plane. For example, a switch can send the device status message to the controller to report its port information. Furthermore, the decoupled control plane is directly programmable, which also brings benefits. For example, if there is a vulnerability in your load balancing application, you don't need to replace any hardware. You just need to patch the centralized logic in the software-based controller. So there is a lot of innovation in SDN, and it is pretty nice. Today, we are going to talk about how to attack the most important part of SDN. Serving as the brain of the network, SDN controller is very important, and attacking the control plane logics may have tremendous promise. However, attacker usually faces two constraints. First, the data plane and the control plane are decoupled. Previously, attackers may attack some critical logics in the switches. However, nowadays all these logics are being placed into the controller. Second, usually only a few components like message handler will be exposed to the data plane. And other applications such as load balancers and diagnostics and web UI will be well protected from the data plane. As a result, data plane attackers usually struggle to find a reachable path to those vulnerable logics. Several recent work also discovered some interesting attacks to reach and attack more control plane logics. For example, the cross-app poisoning attacks leverage shared control plane states to launch attacks from an unprivileged application to a privileged one. So in this talk, we are going to present a novel approach to address the attack reachability problem, which is called D2C2, Data Dependency Creation and Chaining Attack. So unlike previous work that leveraged some existing data flow or SDN schemes to propagate poison data, we choose to create some new and unexpected data dependency to reach some previously inaccessible API. D2C2 provides a new length to examine and exploit the vulnerabilities hiding in the controller. The figure on the right can give you a brief idea on how it works. Don't be afraid of those details and lines in this figure because we will explain it step by step very soon. So the attacker in the data plane will use the compromised data plane device, which is the switch in this case, to interact with the controller. He will inject malicious data, and then a series of components, such as core services and applications, will be exploited in order to build an attack path towards the target. So the new length enables us to discover multiple new CVEs. By launching the attack against four popular SDN controllers, which is Honors, Floodlight, Open Daylight, and SE Floodlight, we found that it actually can introduce serious attack effects, such as network manipulations, data leakage, and denial of service. In total, we have discovered 18 vulnerabilities and got 9 CVE assigned from these vendors. By the time of the presentation, most of these vulnerabilities has been fixed. So before we discuss more details about the attack, let's first talk about the actual attack scenarios. In our threat model, we consider that the data plane devices can be vulnerable. To interact with the controller, the attacker compromises a vulnerable switch or host to perform the protocol interactions. And in such settings, we think the attacker, who does not have direct access to the controller, he wants to introduce attack effects using those limited protocol interactions. So this is a real-world D2C2 vulnerability we identified from honors. The attack effect is to install arbitrary flow tables. To introduce the effect, the attacker needs to attack the flow rule store, which is marked in red in this figure. However, attackers can only interact with the OpenFlow provider, which is the message handling components in honors, using limited protocol interactions. And there is no direct data dependency between the provider and the flow rule manager. Hence, he will go through multiple steps to create several data dependencies and finally reach the attack target. So, of course, in phase 0, the attacker will need to inject the attack payload into the protocol field, which will later become the arguments of a sensitive method. After crafting such a packet, he leveraged the compromised switch to send the message to the controller. Like I said, in phase 1, the malicious protocol field was passed to the handled packet method and generated a poisoned device object. In phase 2, a sensitive method named getDevice in the web UI application will be abused by this poisoned state. By abusing the method, the device object is able to manipulate the web UI application to launch HTTP requests against the API of the flow rule manager. Hence, a malicious data dependency is established from the provider, which is the message handler component, to the flow rule manager. What is a data dependency? In this example, method apply flow rule in the flow rule manager is data dependent upon method get device in UI and is ultimately dependent on the OpenFlow provider. By constructing such data dependencies, attackers can abuse flow rule manager to install malicious flows. By installing flow tables, attackers can do a lot of things in the networks, such as man-in-the-middle attacks. Okay, so such vulnerabilities are big risks, and we should think about the detection. So let's define the problem first. We concluded 4 categories of control plane data items that might be poisoning during the attack, which is protocol messages, network states, databases, and config files. Second, to investigate how control plane components will be affected if a certain data item is poisoned, we study and conclude 2 types of method. The first type of method is called data collecting method, which collect data from the 4 categories. The second type of method is called sensitive method, which will be abused to poison other data items and propagates the attack. Also, the D2C2 consists of many phases, and in each phase, a data collecting method collects poisoned data, and a sensitive method will be abused by the collect data. We call such a procedure as poisoning event. Finally, we will call the chain of events as D2C2 chain. In such a chain, every 2 neighbor events in the chain should have the following relationships, which is the prior event must be able to create at least one data dependency to the later one. So according to this relationship, we try to chain the identified events together. To automatically detect D2C2 chain, we built a tool called SV Hunter. SV Hunter consists of the following three components. First, it takes the controller bytecodes as input and uses a tracer to pinpoint a group of poisoning events in the controller. Then, the reasoning engine reasons the causality relationship between the identifying events in order to create D2C2 chains. The third component is a complementary module to help people synthesize the D2C2 exploits. So the tracer will identify potential poisoning events that can be abused to create malicious data dependencies. Here, we use data flow tracking to pinpoint potentially vulnerable flows from the data collecting method to sensitive method. So as shown in the picture on the right, we will track the code and to find the data flow, which is demonstrated by the red line. And then after identifying poisoning events, which is the code that start from the data collecting method to the sensitive method, our reasoning engine will leverage the program semantics and heuristics to infer what kind of items might be affected by this event. Currently, we introduce architecture-related heuristics for the three mainstream controllers, which is honors, floodlight, and open daylight. And these heuristics are also can be used in their variants. To describe these events, we design a simple but effective declarative language, which is called event reasoning language. The picture on the right is the grammar of the language. And the sentence on the right is from one of running example. As demonstrated in the example sentence, we will use two sub-sentences, which is if and then, to respectively model the precondition and the post-condition of our poisoning events. The precondition described how the events will collect data items, and the post-conditions will describe how a sensitive method will be abused and to poison other data items. First, in the if sub-sentence, reasoning engine will decide that this event collects data from the data plane control messages. Then, the engine leverage program semantics and heuristic to decide that the sensitive method can poison the device objects, which is one of the data items in the controller. And in the last module, to facilitate the complex payload generation, we further visualizing the entire chain. So to figure out how D2C2 can impact widely used SDN controllers and whether SV Hunter is effective in detecting D2C2 or not, we further perform the following evaluation. We implement a prototype of SV Hunter and let it support the three mainstream controllers. Then we test the four controllers and their built-in applications. Here is an overall detection result of SV Hunter. We can see that SV Hunter can effectively generate D2C2 chains for the tested controllers. And in particular, for SE Floodlight, we directly use the heuristic obtained from Floodlight to do evaluation. And SV Hunter can still work well even if SE Floodlight is based on a very old version of Floodlight and its code base can be very different to the newest one. And as shown in the table, in total, we identified 18 D2C2 chains, which leads to 3 serious attack effects. We find 6 chains that can be abused to manipulate the networks, such as we can install arbitrary flows or we can modify some critical states. And we find 12 cases in which we can leak credential data from the controller. For example, we find that we can leak arbitrary files from the file system of the controller. And also, we found several cases that we can disrupt the service or do denial of service attacks. It is worth noting that D2C2 even achieves arbitrary command execution on the honest controllers. So let's discuss a little bit about the potential countermeasures. A very straightforward but effective way is to apply security checks to the vulnerable code. More specifically, we can perform the input validation on the parameters of the sensitive method. Actually, many reported vulnerabilities have been patched in this way. More fundamentally, we may mitigate the malicious data dependency creation. For example, we may enforce dynamic information flow control to detect potential illegal flows. And at the end, a doable approach is to synchronize the protocol interaction. Since the entry point of the D2C2 attack is data plane, and we use data plane messages to send attack payloads, we may synchronize the format and value range of the protocol data fields to eliminate the attack. So here is a conclusion of the entire work. In this work, we present a new attack that abused previously unreachable sensitive method in the control plane. The new attack leads to a discovery of 18 vulnerabilities from the mainstream controllers, and we have helped developers to patch most of them already. Also, we proposed and designed a one-of-a-kind tools to effectively identify D2C2 vulnerabilities. That's all. Thank you.